Hello, my dear students. I welcome you all for this lecture. So, today we will start the new chapter, that is electromagnetic induction. So, in this chapter, we'll study about the magnetic flux, and after that, we'll study the Faraday's experiment and the Faraday's law of electromagnetic induction, Lentz's law, and law of conservation of energy, and expression for induced EMF based on both laws. Okay, both means Faraday's law and Lentz's law. After that, we will study about the methods of producing induced EMF. That is, first one by changing magnetic field, and B, that is by changing the area of the coil, or it is motional EMF. Next, that is by changing the relative orientation of the coil with the magnetic field. And after that, we'll study about the eddy currents, self-induction, self-inductance, mutual induction, and mutual inductance, and some more additional informations. Okay, so these are the brief syllabus about the electromagnetic induction. So today we will see what is meant by the electromagnetic induction. So electromagnetic induction, it is the phenomenon of generating electric current by varying magnetic field. Okay, so we know that suppose you consider the one wire, and at one direction to another direction, suppose the current is passing through that wire, then the surrounding of that wire, the magnetic field is produces. Okay, and here the electromagnetic induction means what? It is the phenomenon of generating electric current by varying magnetic field. Okay, so in this, suppose the one wire, the A to B direction, suppose the current is passing through that, the surrounding of that wire, the magnetic field is produces. Okay, in that case, the using electric field will produce the magnetic field. But here it is the reverse process. Electromagnetic induction means it is the phenomenon of generating electric current by varying magnetic field. Okay, so you vary the magnetic field and produce the electric current. So it is exactly reverse of that wire case. Okay, that is known as what? Electromagnetic induction. So electromagnetic induction is the phenomenon of generating electric current by varying magnetic field. By varying magnetic field. So here the first part we will study about the magnetic flux. Okay, so what is meant by the magnetic flux? We'll see. So the magnetic flux, suppose the magnetic flux through any surface is the number of magnetic field lines of force passing normally through that surface. Okay, suppose consider one surface. Okay, this is the one surface area. Okay, so for this surface area, suppose the how much amount of magnetic field lines passing normally through the given surface in exactly at the B direction. Okay, normal direction, the how much amount of magnetic field lines passing through normally through that surface. Okay, passing normally to that surface, that total number of magnetic field lines that are passing normally through the surface are known as what? Magnetic flux. Or it is having another definition also. It can also be defined as the product of area of the surface and the component of magnetic field normal to the surface. Okay, suppose for this diagram, suppose this is a one surface, okay, and here the exactly at 90 degree, okay, normally suppose the magnetic field lines are passing through this, and suppose the unit normal vector, okay, suppose it is a normal vector, okay, it is a vector, and here the product of the area of the surface and the component of the magnetic field normal to the surface. Okay, suppose the magnetic flux is denoted by phi, then d phi is equal to b dot ds. Okay, that is the b dot ds, and we'll say the ds as a ds n bar. Okay, for a normal vector, okay, you should take the ds as a ds n cap, okay, where n cap is what? It is the unit normal vector, and suppose the b, that is ds cos theta, or it is also phi is equal to b dot a. Okay, so that is the b dot a, where a is what? The vector, okay, it is a vector quantity, or it is a vector of that area. Direction of ds is along the normal of the surface, and where that is that equal to b dot n cap also. Okay, this n cap as a you should take as a, okay, so that is the phi is equal to b into a, okay, or it is also is equal to ba cos theta. So according to this, phi is equal to ba cos theta. Using this relation, we will say the definition, that is only it is the product of area of the surface and the component of magnetic field normal to the that surface. Okay, so here the B is the component that is normal to the surface, and a cos theta is what? It is the area of the surface. Okay, the area of the surface and the component of magnetic field normal to that surface. So it is a definition. So therefore we will say that the magnetic flux is, it is the surface in which the number of magnetic field lines are passing normally through that surface, or it is also defined as it is the product of area of the surface and component of the magnetic field normal to the that surface. Okay, so we'll say, suppose what is meant by the magnetic flux, we'll write that it is the number of magnetic field lines passing normally through the given surface, or it is also defined as it is the product of surface area and the component of magnetic field perpendicular to the surface area. Okay, that is the perpendicular to the surface area or normal to the surface. After that, suppose the here this is the normal to that surface. Suppose B is what? It is the magnetic field lines. that are the normally passing through the surface. Okay, so therefore the product of the phi is equal to B dot A cos theta is the relation of magnetic flux. Okay, the magnetic flux is equal to phi is equal to BA cos theta. So suppose whenever the flux is maximum, okay, when the flux is maximum, when the magnetic flux is maximum and minimum, we will see when the phi is equal to BA cos theta, when theta is equal to 0 degree, when theta is equal to 0 degree, okay, and that time what is the value of cos 0? Okay, so that is the magnetic flux is having the maximum because the cos 0 value is 1. So phi is equal to B dot A. Okay, flux is maximum when theta is equal to 0 degree and the phi is equal to B dot A. So in this case the flux is maximum. Then when the flux is minimum, when the magnetic flux is minimum, that time the theta is equal to 90 degree. When theta is 90 degree, that time flux is the minimum. So therefore the flux is maximum when the theta is equal to 0 degree because BA cos theta, so that is equal to B dot A, and the flux is minimum when theta is equal to 90 degree. Then what is that positive flux? Okay, the positive flux is a positive for 0, that is the less than or equal to theta, and that is the suppose the greater than 90 degree. Okay, so suppose you should take 0 to 90 degree. Okay, in this case suppose the 0 to 90 degree, in this case, or 270 to 360 degree. Okay, in these two conditions the positive flux is present. Okay, the flux is present, magnetic flux is positive when the theta to 90, theta value will be 0 to 90, or it is 270 to 360. Okay, in this range this is a positive flux. When the flux is 0, okay, 0 flux, when the magnetic flux is 0 for theta is equal to 90 degree and theta is equal to 270 degree. Okay, so theta is equal to 90 means it is a exactly the on the surface. Okay, here it is on the surface, and the theta is equal to 270, it is downward direction, it is also on the surface of given surface. Okay, so the flux is 0 whenever the theta is equal to 90 degree and the theta is equal to 270 degree. Then when the flux is negative, okay, the negative flux is there whenever the theta is here more than 90 and it is a less than 270. So whenever the theta is 90 to 270, okay, in this range, okay, it is a negative flux. So therefore the magnetic flux, it is the magnetic flux through the any surface is a number of magnetic field lines passing normally through the given surface, or it is also defined as it is the product of area of the surface and the component of magnetic field normal to that point. Okay, and the here it is suppose the one surface, given surface you should take, and at B direction the normal direction. The all magnetic field lines are moving in this, okay, passing through this, and therefore the phi is equal to BA cos theta. Phi is equal to BA cos theta. This is the condition of the magnetic flux. So the magnetic flux equation, phi is equal to BA cos theta, where the B is what? B is the magnetic field direction, okay, that is a magnetic field direction that is normal to the given surface, and A is a, suppose that is a unit vector, okay, or it is also known as area vector. So uh, here the BA cos theta, that is equal to the magnetic flux, and the flux is maximum whenever the theta is equal to 0 degree, and the flux is minimum whenever the theta is equal to 90 degree, and the positive flux is there whenever the theta in between 0 to 90 degree, or it is 270 to 360 degree, and the flux is zero flux whenever the theta is equal to 90 degree and the theta is equal to 270 degree, and it is negative flux when the theta is a 90 to 270 degree. After that, the phi is equal to BA cos theta. It is the equation for the magnetic flux. So using this relation, the magnetic flux across a coil can be changed by a changing. Okay, so the flux can be changed. Phi can be changed whenever the B will be changed, whenever A will be changed, or the theta will be changed. Okay, the phi is depend on B, A, and theta, all three. So therefore, the magnetic flux is the depends on the some factors, that is the first one, the strength of the magnetic field B. Okay, it is depends on the strength of the magnetic field B, and it is also changed the area of cross section of the coil A. Okay, the area of cross section of coil A, and it is also the orientation of the coil with magnetic field theta, okay, or any of the combination of the above. Okay, so here it is depends on the main three factors. One, strength of the magnetic field. Next one, area of cross section of the given coil, and the theta. Okay, theta is the orientation of the coil with the magnetic field, or it also depends on the any combination like B and A, B and theta, A and theta, or else BA theta, all. Okay, it depends on these three factors, mainly three factors: B, A, and theta. Strength of the magnetic field, area of the cross section, or the orientation of the coil with magnetic field. Then the magnetic flux is a scalar quantity. Okay, so it is a scalar quantity, and the SI unit of magnetic flux is Weber. Okay, the SI unit will be Weber, or it is also the Tesla meter square. Okay, so it is, that is the magnetic field is Tesla and a area is meter square. So it is Tesla meter square, also the SI unit of magnetic flux, or another one is Weber. And the CGS unit of magnetic flux is Maxwell. Okay, the CGS unit of magnetic flux is Maxwell, and the one Maxwell is equal to 10 raised to minus 8 Weber. Okay, the relation between the Maxwell and Weber is what? The one Maxwell is equal to 10 raised to minus 8 Weber. And the magnetic flux that is associated normally per unit area is called the magnetic flux density, or it is also known as strength of the magnetic field, or it is a magnetic induction. Okay, so another definition, okay, it is what? The magnetic flux per unit area is also known as the magnetic flux density, or it is the strength of the magnetic field, or it is a magnetic induction. So we will discuss this experiments of Faradays and Henry's to study the electromagnetic induction. Okay, and the current, there will be the three experiments are there. Okay, the Faraday and Henry to study the electromagnetic induction. They performed the three experiments, and the first experiment is the current induced by a magnet, that is coil magnet experiment. Second one is current induced by a current, that is coil experiment using two coil experiments. And current induced by a current, that is a again coil experiment. So the three experiments, first one is current induced by a magnet, second one is current induced by a current, and third one is current induced by a current. Okay, so current induced by a current, here that is the actually changing current. Okay, that is the current induced by a changing current. Suppose the here they should take, this is a coil. Okay, suppose this is a one coil, and that is one end is connected with the galvanometer one end, another end of the coil is connected with the galvanometer another end. Okay, and whenever the one bar magnet, okay, you should take the bar magnet, when the bar magnet moving closer to the this coil, and they are taken another one coil. Okay, so here again the same condition, they are taken the, suppose the galvanometer at one end, another end, another galvanometer. Okay, whenever the north pole of the this magnet N and S, okay, two poles are there, the north pole of this magnet, okay, when the moving to the coil 1, okay, first coil, that time what happens, the here whenever it is the N pole is coming closer to this, so this coil behave like a N pole, and here the galvanometer shows some deflection. Okay, whenever N pole coming closer to this coil, it shows more and more deflection, and whenever S pole is moving away from this, it is moving this direction, means obviously S pole is moving away from this coil, that time the galvanometer shows opposite deflection as compared to this coil. Okay, so therefore the whenever the coil, okay, the first coil is connected with the galvanometer, then the, suppose the N pole of the bar magnet coming closer to this, that time the current is flowing in a anti-clockwise direction in this coil. Okay, and the whenever S pole is moving away from the second coil, that time the clockwise direction the current is moving in this. Suppose you should take the bar magnet as the opposite. So suppose S pole you consider closer to this first coil. Okay, whenever the S pole is coming towards this coil, then the current flowing in this coil will be, suppose the galvanometer shows some deflection and the current flowing in this coil is the clockwise direction, and after that whenever N pole moving away from the coil 2, that time the current flowing in it will be anti-clockwise direction. So here the suppose the N pole coming closer to the coil, this behave like a N pole. Okay, this end behave like a N pole, and that time the anti-clockwise direction the current is flowing in it, and here the same second coil is suppose behave like a N pole, this end behave like a N pole, and this is a clockwise direction the current is moving in this. Okay, so as compared to this segment, okay, here the only the bar magnet direction is opposite. S pole is here, N pole is here. The whatever this segment, okay, will be observed exactly opposite to this, it is observed. So like this the Faraday's experiment, first experiment is performed. In this experiment, suppose they are taken initially one coil, okay, this is a coil, and that is connected with one end is connected with a galvanometer one end, and another end is connected with a galvanometer another end, and they are taken the bar magnet. Suppose N pole taken closer to the coil. Whenever the coil is moving closer to this, okay, that time what happens, the here in this coil, okay, the suppose the current is moving in this coil, so using magnetic field we are producing the current in the coil, and this end behave like a N pole. Okay, this end behaves like a N pole, and after that the magnetic flux linked with the coil changes with the relative to the positions of the coil and the magnet due to magnetic field lines. Okay, so what happens, the magnet is having magnetic field lines, whatever the blue lines shown here like this. So these magnetic field lines are whenever taken N pole closer to the coil, that time they all the magnetic field lines will be inserted in this coil, and here we are connected one wire to the galvanometer, so the galvanometer shows some deflection. If the galvanometer shows some deflection means the current is present in the coil. Okay, the meaning of this will be the current is present in the coil. So here in this experiment, when the north pole of the bar magnet, okay, when the N pole, north pole of the bar magnet is the taken towards the coil, okay, north pole whenever taken towards the coil, that time the galvanometer shows deflection in one direction. Okay, the galvanometer shows deflection in one direction, and this indicates the current is present in the coil. Okay, suppose the galvanometer shows some deflection means obviously the here in this coil the current is present. So therefore, the current is present in the coil whenever the galvanometer shows some deflection. That is the meaning. After that, when the north pole, okay, you should move away from the coil. When the north pole moves away from the coil, okay, that time the suppose whenever the north pole pulled away from the coil, the galvanometer shows deflection in opposite direction. Okay, the galvanometer shows deflection in opposite direction. This indicates the current is induced in the opposite direction. Therefore, in the coil, the exactly opposite direction the current is flowing in it. When the magnet is brought to rest, okay, whenever the magnet is at rest and the coil is also rest, so in that condition, the galvanometer shows zero deflection. Okay, whenever the coil and magnet at rest position, that time the galvanometer shows zero deflection. After that, when the south pole of the magnet is moved towards the or away from the coil, then the galvanometer deflections are opposite to the those observed in the north pole. Okay, so suppose the north pole, if you take as a this direction, suppose south pole, that time what happened? When the south pole of the magnet is moved to the coil, okay, the galvanometer shows exactly opposite that to the north pole, and the deflection will be exactly opposite. It is observed. Then after that, the deflection of the galvanometer is large whenever the magnet is comes faster towards or away from the coil. Okay, suppose the N pole is coming faster to the coil, that time the deflection will be more. Suppose the N pole is moving faster to the coil, that time also the galvanometer shows more deflection. When the coil is moved keeping the magnet at rest, okay, suppose you should consider magnet at rest and this coil you take closer to the N pole, that time also the same effects are observed. Okay, so again, whenever the bar magnet is constant rest state and coil coming closer to this, that time the here it shows the galvanometer in deflection one direction, and whenever the coil is moving away from this, that time the galvanometer shows the opposite deflection. Okay, like this the coil magnet experiment, okay, that is current induced by magnet experiment is observed. Okay, so here we'll see the arrangement consists of a coil with a galvanometer and a bar magnet. Okay, the galvanometer is connected with the coil and the bar magnet is there. When the north pole of the magnet is pushed towards the coil, the galvanometer shows deflection in one direction. This indicates the current induced in the coil. Okay, whenever the N pole closer to the coming closer to the coil, that time the galvanometer shows some deflection. It means the current is induced in the coil. Then second one, the magnet is brought to rest, the deflection of the galvanometer reduces to zero. Okay, suppose the magnet is a motion state, then only the galvanometer shows some deflection. Suppose the magnet is brought to rest, that time the deflection is reduces to zero. Okay, and when the magnet is pulled away from the coil, okay, that time the galvanometer shows deflection in opposite direction. This indicates that the current is induced in the coil. Okay, and it is opposite direction. And then after that, when the south pole of the magnet is moved suddenly towards or away from the coil, the galvanometer deflection are opposite to those observed with the north pole. Okay, for north pole, whatever the observation is there, exactly opposite to that south pole observations are there. Okay, so observations means here you should take the closer whenever the magnet and coil you should take the closer. Okay, towards the towards that time the deflection will be more and it is at one direction, and whenever the magnet is moving away from the coil, that time it is the opposite direction current is flowing in the coil. Then the deflection of the galvanometer is large when the magnet moves faster towards or away from the coil. Okay, so if the velocity of motion of that magnet is more, okay, that time the faster moves towards or away from the coil, that time the deflection of the galvanometer is more. And when the coil is moved, keeping the magnet at rest, the same effects are observed. Okay, so like this, the first experiment is conducted by Faraday, and the main observations of this experiment is the relative motion between the coil and the magnet. Okay, so the main observation is the relative motion between the coil and the magnet that should be observed, and second one, that is the induced polarities of the magnetism in the coil. Okay, so how much amount of the current is moving, okay, that they should observe, and after that the direction of the current through the galvanometer and hence the deflection in the galvanometer. So if the deflection in the galvanometer is more and one direction, then the coil or magnet is moving towards, and whenever the magnet is moving away from the coil, that time the galvanometer deflection is exactly opposite, therefore exactly opposite direction the current is moving in it. So next one, that the induced current EMF is available only as long as there is a relative motion between the coil and the magnet. Okay, the induced current EMF is available only as long as there is a relative motion between it. Okay, so like this. Then the note, the coil can be moved by fixing the magnet. Okay, so you should take fix magnet and coil is moved. Both the coil and magnet can be moved towards each other or away from each other. That is, there must be a relative velocity between them. Okay, and the magnetic flux linked with the coil changes relative to the positions of the coil and the magnet, and the current and hence the deflection is large if the relative velocity between the coil and the magnet, and hence the rate of change of flux across the coil is more. So see here, the coil can be moved with fixing the magnet. Okay, magnet you take as a constant state, and the coil is moved. The both coil and magnet can be moved away or towards. There must be a relative velocity between them. Then only the current is induced in the coil. And the magnetic flux linked with the coil changes relative to the positions of the coil and the magnet. Okay, so the flux linked in that coil will be changes with the relative position of the coil and magnet. And the last one, that is current, and hence the deflection is large if the relative velocity between the coil and magnet, hence the rate of change of flux across the coil is more. Okay, the rate of change of flux across the coil is more when the relative velocity between the coil and magnet is large. Okay, so means the coil and magnet are moving faster, that time the current produces in the coil is more. Because of that reason, the change in flux present in that will be more. Okay, so the change in flux across the coil is also more. Like this, the some observations are there for this experiment. So this is the Faraday's first experiment. Okay, so we'll see the second experiment in next time. Okay, thank you.